Let us go to the example of methane. So, here is a methane molecule. It is a very simple molecule with 1 carbon and 4 hydrogen, and if I want to perform a calculation on 631G basis set, we are going to of course actually going to perform a calculation on it to show you that whatever you understand from the theory is same as what you get from a calculation. Now, let us take the example of methane. So, first it has a carbon, and so basically it has 1s. 631G is a double zeta basis set. So, the valence orbital I will now expand it into two sets of stator type orbital, 2s 2s dash and 2p dash. Now, 631G, that means this will be 1s will be expanded in 6 Gaussians, this will be expanded in 3 Gaussian, this will be expanded in 1 Gaussian, 2p will be expanded on 3 Gaussian and 2p dash will be expanded in 1 Gaussian. Now, how many Slater type of orbitals are there? One for the core, 2 for the 2s orbitals. Now, there are 2p and 2p dash. Remember, each p orbital has px, py and pz. So, this will be total 6 orbitals. Now, think of hydrogen. Okay, let me calculate the Gaussians also. So, 6 Gaussian from the core, 3 Gaussian from 2s, 2 Gaussian from the 2s dash, there is 1 Gaussian. The first one will be total 9 Gaussian, 3 times 3, and the third one will be 3 Gaussian due to 3 p orbitals. So, it is 10, 9, 3, it is 22. Now, hydrogen. So, for hydrogen there is no core orbital, the only electron it has is valence electron. So, in this case I will have 1s, 1s dash. The first one I will expand in 3 Gaussian, the second one I will expand in 1 Gaussian. So, my number of Slater is 2 and my number of Gaussian is 4. So, I have now total, this was 9. So, my total STOs are 9 plus 2 into 4, 4 hydrogen. So, total 17 and total GTOs, I should have written the S here also. So, in this case it was 22 plus 4 hydrogen, so total 38. So, if I perform a calculation with this orbital, it should give me total 17 STOs and 38 GTOs, and we will see from one of the Orca calculation, if I do calculation on the same molecule, do I get the same results or not. So, now for come to 6311G basis set. So, for carbon, this is how one should write it. So, this is a split valence basis set again. So, it is 1s. For the 2s I will have 3 of them. So, 2s, 2s dash, 2s double dash, and for the same thing will be for the p also, 2p, 2p dash 2p double dash. So, let us first calculate the STOs for carbon. So, 1 plus 3 for 3s, and then total will be, there are 3 p functions, remember, and each of them will have a 3 set. So, number of STOs will be 13. So, it is 1 plus 3 plus there are 3 p orbitals, so total 9 is fine. Now, let us look at the Gaussians. So, this will have 6, right, this will have 3, 1, 1. Now, 2p, because 3 of them and each of them is 3, so it is 9, this is 3, this is 3. So, total it is 6, 3, 9, 10, 11, 20, 26. Now, about hydrogen. Remember, for hydrogen the 1s orbital is valence. So, it will be 1s, 1s dash and 1s double dash. So, STO is 3, and now look at the GTOs. So, this is 3, this is 1, this is 1. So, now this total GTOs for the number is 5. Now, what is the total number of STOs? Remember, there are 4 hydrogens, so it is 25, and my number of GTOs 26 plus 5 into 4 . So, my total number will be now 46. So, the present form of the function, if I write only in terms of STOs, it has 25 STOs. So, that will be my final number of my basis functions, and number of GTOs will be 46. So, we will do the calculation, but before that let us try to see what other kind of functions is required beyond going to double zeta, triple zeta. Of course, I can go to quadruple zeta, I can go to pentaple zeta, but just increasing the number of functions does not really help, because chemistry tells us that just doubling of the function is not going to do. Different orbitals has different nature for their calculations. So, we need to extend to what is called a polarization function, and what these polarization functions are, we know that the K shell is n is equal to 1. So, it has only s orbital, L is n is equal to 2, has s and p orbital, M has n is equal to 3, so s, p and d orbital. So, what happens in the case of polarization function is that you actually put one angular momentum higher function. So, for hydrogen and helium you will p type of functions, for lithium and calcium you will put d type of functions, and for transition metals you will put f type of function, and so on. And why you put this polarization function is that this orbital can distort and adapt better to the molecular environment. With the basis sets which contains polarization functions, the examples is double zeta polarization DZP or split valent polarization SVP, like this. And you also have this Popel type of basis set where you can add polarization. So, I can take a standard 631G, and if I add p function to the hydrogen, because for hydrogen the electron is 1s. So, the next angular momentum function is p. So, if I add p type of function to the hydrogen and d type of function to the carbon, for methane it will call 631G star star. or sometimes it is represented as 631G dp also, because you have added d type of function for the heavier element and p for hydrogen. If you just add the d function for the heavier elements and keep the hydrogen as it is without any extra polarization function, that is called 631G single star or 631GD. So, this is generally a standard practice, that for hydrogen it is generally okay to, because it has a spherical symmetry, it is generally okay to use a slightly smaller basis set than the heavier element. Now, if you want to understand in terms of the chemical intuition why you need these polarization functions, think of the example of water. If I just use the 631G basis set, you can do the counting. So, my oxygen will have s and p orbital and my hydrogen will have s orbitals. Now, you see, to have the hydrogen overlap with the p orbitals we know it looks like a dumbbell. So, in this condition the overlap will not be very effective. But if I add with this p orbital a little bit of d functions, then my resultant orbital shape will be like this. So, this effective overlap between the orbital will be much better if I use a higher angular momentum functions. That is why generally polarization functions are essential to get meaningful results, especially geometries in the case of getting bigger basis set. So, just increasing the number of the zeta functions is not good enough, you need to increase it meaningfully, and one of the good option to increase the basis set is to add polarization function to the basis set. Now, the next thing you can add is diffuse function. Most of the cases the basis sets are usually concentrated on the inner shell of the electron, because core electrons they are very tightly bound. So, in this case if they are not so much important in the case of chemical properties. So, the tail of the wave functions is not really a fact. But if you are going for anions or excited state where the electron density is away from the nuclear framework, in that case the tail of the wave function is very important, and in that case you need to put diffuse function. So, you have to supplement, or in the language of basis set it is often called augmentation. Augmentation essentially means supplementing the basis functions with diffuse function. Diffuse functions mean it has a small exponent value, so that decay very slowly. So, if I add basis function to my basis, so now what was decaying here it will decay much more slowly. And when I just add to this diffuse function to hydrogen, that is called plus, and when I add it to the other elements also, they are called plus plus. So, plus plus essentially means I have added the diffuse function to the hydrogen as well as for the other element. If I take the let us say 631G plus plus, so in that case my valence orbital has two 1s function for 2 and 1, because it is a double zeta basis set. The first one will be expanded in 2 Gaussian, the second one will be expanded in 1 Gaussian. I will also add another s functions which actually will have a very small exponent that is diffused, and now it will be 3 basis functions. So, now if I think of carbon atom, if I go back to my previous example, I knew originally my basis function was 1s, 2s, 2s dash, 2p, 2p dash, and 3 of them will be there because px, py and pz. So, in this case to put the diffuse function, so I need to put an extra 2s as well as one extra 2px, 2py and 2pz. So, as a homework problem, I give you the problem to count the number of Slater type of orbital and Gaussian type of orbital for methane using 631G plus plus star star basis set. So, you should try this at your leisure and try to find out how many number of Slater type of orbitals and Gaussian type of orbitals are there in your basis function. Now, the basis functions what I was showing up to now, they are mostly Pople kind of basis function. They were developed by John Pople, the famous Nobel laureate. But if you want to use electron correlation method, we have not discussed what is electron correlation method, we are going to discuss that next week. But if you want to use electron correlation method like MP2 or couple cluster, you need to use Dunning's correlation consistent basis set. Now, these basis set are augmented with functions with even higher angular momentum. So, in Pople kind of basis set, when I was putting the polarization function, they are generally one angular momentum higher, but here you put even higher angular momentum basis functions. they are like CCPB DZ, CCPB TZ, CCPB QZ. This is how the nomenclature is. Just look at the form how they are written. This is a convention. So, the CC is small, this is correlation consistent. P is also small, that is called polarization, valence, double zeta. So, that means it is a correlation consistent basis set, it has polarization function and valence orbital has 2 zeta functions. Similarly, this is CCPV TZ, CCPV QZ, pipe Z, in some of the cases it has up to 6Z also. Now, these are the normal basis set. This basis set can be also augmented with diffuse function by just putting a keyword AUG, small AUG. So, this will call augmented CCPV DZ. This is the augmented version, diffuse function augmented version of the normal CCPV DZ. This is the diffuse function augmented version of normal CCPV DZ, so augmented CCPV DZ, augmented CCPV DZ. This basis set should be used with frozen core calculation. So, the way these basis sets are parameterized in such a way that you should freeze the core electron, and to do the get an accurate energy, it is not necessary to have the core electron included in your calculation. So, remember, if you are using this kind of basis set for calculation, remember to freeze your core. And this basis set advantage is that because these are systematic, it has a cardinal number. So, this DTQ is called cardinal number. So, how many zeta functions you have? Because these basis sets are systematic, it is double zeta, triple zeta, quadruple zeta. So, I can actually calculate few of them, maybe double zeta, triple zeta, quadruple zeta, or double zeta, triple zeta, quadruple zeta, and then I can fit to one functional form and extrapolate it to the infinite basis set limit. We are going to know about the basis set extrapolation technique modes in the following lectures. So, these basis sets are ideal for basis set extrapolation, and in many of the cases these kind of basis sets are used for basis set extrapolation. Now, as I told before that this basis set should be used for frozen core calculation only, but in certain properties the contribution from core electrons are very important. So, in that case you need to use the core correlated version. They are parameterized in such a way that they reproduce the correlation of the core electron very accurately. So, in that case they look very same, but these are called CCPCVTZ, correlation consistent polarization core valence triple zeta. So, what happens in the that is corresponding augmented version is there. So, you have seen that in case of the normal basis functions, we generally reproduce the core by only one type of orbital, with the hypothesis that the core orbitals will be less important for most of the properties. But to describe the core orbital properly, I need to use more than one valence type of orbital. So, more than one sided type of orbital, that is what is done in this kind of basis set. So, this gives a very accurate value for the core correlation, of course, at the expense of much larger computation cost. Now, these are the values for this hydrogen, what are the primitive functions for the hydrogen and other elements. We are going to go into this discussion, we will go to the basis set exchange and we will see what this correlation consistent basis set looks like and what does it mean by this 2s1p, 3s2p, 1d like this. But before discussing that, let us discuss something called an effective core potential. So, effective core potential are a meaningful way of replacing the core electron with an effective potential, eliminating the need for extensive core basis function, which is typically requires numerous Gaussian function for accurate representation. Remember the basis set 631G or 6311G. To reproduce the core orbital, we have put 6 number of Gaussian functions. So, what you do with the effective core potential is that you replace those basis function and actually put a very simple potential of this form, so that the core electrons are replaced, but this potential actually reproduce the behavior of the core electron, and that reduces the computational cost in the quantum calculation, especially for heavier atoms, because their core can be large number of orbitals. And this can also parameterized in such a way that it can reproduce a scalar relativistic effect, or in some of the cases the modern ECPs, it can also take care of the spin orbit coupling effect. So, you can actually take, not only it reduces the computational cost, it actually helps you to get to the effect of the relativity in your calculation without actually doing any expensive method. They are good alternative to scalar relativistic all electron calculation if heavier elements are involved, and They are very effective, especially for geometry optimization and energy calculation, but for all properties, especially for properties, the contribution of core electrons are very important. In that case, the ECPs may not be so effective, and for that you have to use the so called scalar relativistic all electron calculation, more expensive, but we will discuss some cases like that. And to minimize the computational effect, the heavily contracted and chemically inactive core based function can be replaced by ECPs, and these calculations are actually called a valence only basis set, and generally they are rely on the Fusen code approximation. Now that leads to the turbomole DEF2 basis set. DEF2 is a more modern family of basis set. They are very popular these days, and why they are called DEF2 is that because they are the turbomole second generation default. Because it's default, it's DEF, and second generation default, there was a first generation default which was normally used to call DEF. These basis sets are more modern, so these are sometimes called Karlsruhe basis set also from the place where the software turbomole has originated. So these are second generation default, that's why DEF2. So this DEF2 basis set forms a system of segmented contracted basis set for the elements hydrogen to Rn for different level of flexibility and accuracy. And one of the particular properties of this basis set automatically uses ECPs for atoms beyond krypton. So the advantage is that this basis set is almost available for the whole periodic table. So you can use the same basis set for all the elements you want to do calculation upon, which is not the case in many of the basis set, where you will not see it for all the elements you want to do calculation upon. The second advantage is that they are designed to give similar errors all across the periodic table of a given basis set type, and you will see the nomenclature DEF2 SVP. DEF2 is second generation default. Its SVP is for single valence polarization, like let us say quadruple zeta valence polarization. This is how the nomenclature goes. And the advantage is that at the Hartree-Fock or DFT level, this extended QZVP basis set yields atomization energies within the 1 kilojoule per mole with respect to the complete basis set limit. So basically what this basis set serves the purpose is that in a smaller dimension they generally gives you very accurate answers. So this is the error in the atomization energy with respect to the complete basis set limit values. So that means with a smaller dimension of the basis set also you can get very accurate results, and that is why these basis sets are very popular in the present time. So if you want to do Hartree-Fock or DFT calculation, it is advisable that you do this kind of basis set calculation. Now before ending this topic and starting our calculation, the question is that how to choose an appropriate basis set for your calculation. So if you ask me, the easiest recipe is to see bada hai to behtar hai. So the bigger is your basis functions, for those who do not understand Hindi, the better is your calculation. So the more the dimension of the basis set, accurate is the answer. In principle that should be infinite, but of course it depends upon what kind of computers you have access to. Infinite basis set is of course not possible, but very large basis set calculation, especially if you are using very accurate wave function based method, may not be a very straightforward thing to do. So but then the question is that how you are going to choose it. So you have to choose a basis set which gives you the best approximation between computational cost and accuracy. There is no direct answer to this question how to choose the best basis set, but of course we can provide you with some guidelines. The first thing is that be aware of BSIE, basis set incompleteness error, and basis set superposition error. We are going to discuss what these are in the next week. So basis set incompleteness error means your result has still not converged with respect to the basis set, and superposition error is mostly problematic when you are doing calculation on more than one molecules or a dimer. So you should be careful about them. The second thing is that you should try to approach a reasonable basis set, at least triple zeta quality for energy related properties if you are using Hartree-Fock or a DFT method, triple zeta or higher. So the Hartree-Fock and DFT methods generally converge more quickly with respect to the basis set than the so called electron correlation methods like MP2 or couple cluster or CI or CAS-SCF. So if you are using any of this method, MP2, couple cluster or CAS-SCF, you have to at least use the quadruple zeta quality basis set or somehow need to go to complete basis set limit by doing extrapolation. DFT, most of the cases the triple zeta basis sets are good enough. So, if you are doing a triple zeta calculation in DFT, most of the cases you are good enough. If you are using a wave function based method, make sure you are using a CBA scheme, because even a quadruple zeta, when I say quadruple zeta basis set, it is reasonable, but there are cases when the energies or the properties will not converge even with a pentapole zeta basis set. So, you have to somehow use a complete basis set extrapolation scheme for the wave function based method whenever you are using it. Next thing, if you are interested in getting good geometries, want to get good properties and good energies, make sure that you add polarization function for flexibility. If you are interested in anions, if you are interested in excited state, dipole moment, polarizability, you have to make sure that your basis function have sufficient number of diffuse functions. Without these diffuse functions, these properties will not come. Dipole moment, polarizability, excited state, anions, they will not come correct. And most importantly, check for basis set convergence. Once you get a result with a reasonable quality basis set, let us say triple zeta, quadruple zeta, make sure that increasing the basis set by one cardinal number, make it quadruple zeta or making it double zeta, does not changes the result drastically. So, there should not be any qualitative change in the result. If by changing one cardinality, going from double zeta to triple zeta to quadruple zeta, changes the result qualitatively, that essentially means that your calculations has not converged with respect to the basis set value. So, you need to do some kind of an extrapolation, think of a bigger basis set to get to the more accurate result. You should not trust your results if it is changing very rapidly with respect to the change in the cardinal number. And if the heavier elements are present, make sure that you use effective core potentials. It serves two purposes. It allows you to use larger basis set for the valence orbitals. Secondly, it takes care of the relativistic effect. If Z is more than 36, then the relativistic effect will be very important for the whatever you are calculating, the energy or the properties. So, you have to make sure that you use effective core potentials for doing the calculations on heavier elements. And moreover, always search the literature to see what other people have used. It is not always correct that other people have used a better basis set or they know how to do it, but at least it gives you a first approximation what kind of basis set needs to be used for your system.